Yes, hi guys. So we were talking about question number 6 now. Now question number 6 said, in the first quadrant of the circle, x square plus y square equal to a square, the surface density varies at x by. Okay. Now find its moment of inertia about the x-axis. So here the density, let me write it, this is the axis, let me take x-axis, y-axis, y-axis, x-axis. Now this is semicircular axis. In the first quadrant of the circle, or x is equal to y square equal to a square. This is the circle here. Let me take. This is the circle here. Here, the distance is a. In this case, up to this point. And if I draw a parallel strip to the axis of y coordinate will be here. We will find out y coordinate along this axis. Here y equal to 0. Now, if this circle is x square plus y square equal to a square, a is the radius of the circle, and center is 0, 0. Okay. Now from this, y can be calculated as y equal to under root a square minus x square, a square minus x square equal to y square, or y square, or y equal to under root of this. Here y is equal to square root a square minus x square, will substitute the value, and here x equal to 0, x equal to a at this point. If I find out the x coordinate, then we draw parallel strip to axis of x. Here x equal to 0, and here x equal to a. Here it is a0. Here is the radius, total a radius, 2x equal to a. Here the coordinates, limits of x and y respectively. Y limits are x, y equal to a2, y equal to 0, sorry. Y equal to 0 to a is its radius. Okay, y equal to 0 here on the axis of x. Y equal to 0 on the curve. This is semicircular arc. So here y is equal to 1 to a square. Now, so these are the limits of the equation. Now we have to find out what is given. Density given. What is given to us? Sorry, given or what is written? Let me write here. Given a circle, semicircle. Okay, in the first quadrant, as x square plus y square a square. This is circle given to us. Area, if we have to find out of the circle, that will be pi a square upon, because a is the radius, pi a square upon 2, half of the semicircular area. So, I mean, sorry, not area. We have to find out this quadrant, semicircular arc. This is semicircular arc here. Okay. Here it is given. In the first quadrant of the circle base, the surface density varies at x by. Find its moment of inertia about the x-axis. This is the first quadrant only in the first quadrant of this semicircular. This arc, not semicircular. Semicircular is like this. And only in the first quadrant it is given. Semicircle in the first quadrant, semicircular arc we say. Semicircular. This is semicircular arc. This is semicircular arc. In the first quadrant, the surface density varies as this. Surface density rho, let me take equal to lambda into x by. This is x by varies as x by. So rho is proportional to x by, or rho equal to lambda x by, where lambda is constant of proportionality. Where this lambda is constant of proportionality. Constant of proportionality. Okay, now we have to find out what is the M.I. moment of inertia. Solution. Now let me find out. Solution. In the first quadrant we have to find out. Find the moment of inertia about the x-axis. About the x-axis. This is x-axis here. About the x-axis, we know that what is the moment of inertia. M.I. Let me write here. Sigma m is the mass r square equal to double integral sign. Okay. This is area integral, surface area. This is about the x-axis we have to find out. Axis is y square into rho into ds dy. now we have to write the limits and everything. For the limits of x coordinate first, let me write x is 0 to a. 0 to a. Second limit is y. Y here is 0 to. Okay, that is under root a square minus x square into y square. Rho density is lambda into x5 into d of dy. Okay, now let me find out this. 0 to lambda is constant are taken outside. 0 to a first limit 0 to under root a square minus x square. The y square into y is y cube. Okay, if I integrate this with respect to y, because the limits here are 0 to under root a square minus x square, that means in terms of variable x. First we have to integrate it with respect to y. Okay, into dx. This will give us lambda 0 to a integration y cube or y4 upon 4 integration limits 0 to under root a square minus x square into dx. Now putting the limits, substituting the limits here. Limits after substitution of limits, we get lambda 0 to a upon 4. If I take outside this 4, in place of y we have to substitute the upper limit only, because at 0 it is 0. The upper limit is under root a square. This is 4 times, that means a square minus x square whole square is into x. Where is x? I'm sorry, this x is also there. X into this x is also there. Right here x. Here x is also there into dx. Why this x is there? X into y. Y cube. Y cube we are taking, x is also there into dx dy. Alright, now this can be further resolved as lambda upon 4 constant 0 to a. If I open the whole square and then multiply by x, then integrate with respect to x, that will give us the solution. Let me first open the whole square. This is a4 plus x4, or let me take middle term, which is minus twice a square x square plus x4 into dx. Okay, now multiplying lambda upon 4, 0 to a limits. Multiplying by x, we will get a4 into x minus twice a square into x cube plus x5 into dx. Now integrating it with respect to x, what do we get? Let me solve it here. Finally, this is only with respect to x. Find its moment of inertia. What the x-axis? No problem. We are finding out what the x-axis. Lambda is equal to, sorry, this mi equal to mi about axis of x, mi about x-axis is equal to, we are calculating this lambda by 4 outside, sorry, this lambda by 4 here, and take 0 to 8 limits. Okay, this is write it clear. Lambda by 4, 0 to 8 limits. Here we have option. Now this integrating a4 into x, that means a4 into x square upon 2 minus twice a square into x4 upon 4, because x cube integrated as x4 upon 4 plus x5 integrated as x6 upon 6. Sorry, this is x5 okay, x6 upon 6. Because x square here, x4 into x into 14, that's 5. Then integrated as x6 upon 6, 4. Now putting the limits, this is now 0 to a. Integrated now, it is integrated. Limits are 0 to a, we have substituted 0 to a limits now. After substituting limit 0 to a, let me take what is the answer of it. 0 to a, putting lambda upon 4. This is in bracket a4 into a because a upper limit only is to be substituted here by this. Okay, so if A6 was A square upon 2 to the 4, 1.2 only A square into A4 upon 2 plus A6 upon 6. Solving it now. So finally what we get? Now let me solve it further. Therefore Mi with respect to or about x-axis is obtained as A6 upon 2 minus A6 upon 2. Okay, plus this is A6 upon 6. These two are cancelled out. A6 upon 2 and minus A6 upon 2. We will determine this term first. Only this value is open. This is lambda A6 upon 6 4 is 24. This is Mi here. Lambda into A6 upon 24. This is the, let me take first equation. Only this Mi is to be calculated. Now, if we have to find out what is the mass here, the mass of this circular lamina is given by, if I find out mass, then mass equal to 0 to same limits 0 to A, x limits, y limits 0 to under root A square minus x square into lambda xy. This is the density here. Lambda xy is unit elementary density, I mean, or mass of the element. Lambda into xy. Go see the density, which varies like this into dx. Because first we have to integrate it with respect to y. Here is no y or x, y square or x square. Only this is the mass here. But the mass comes from 0 to A. If I integrate this y with respect to y, so it will be lambda, let me take outside. It's x into y square upon 2, 0 to A under root A square minus x square. Y limits 0 to A. And this is dx here. Okay, so this is Mi, moment of inertia with this value. Now, if I find out the mass, then we separate that mass into the perpendicular distance. That is how much mass I am just calculating. Therefore, the mass of the lamina, circular lamina here in the first quadrant is equal to this lambda into 0 to A into x. Now putting the value here upon 2, let me take this 2 outside and putting y square is this, so this is nothing but A square minus x square into dx now. Because this is square root will be considered, it is whole square, y square. In place of y square, if I substitute square root A square minus x square, then whole square, that means square root and square cancel out. Now integrating first lambda upon 2, integrating x into A square, that means A square into x square upon integration. This is x cube integrated as x 4 upon 4, 0 to A limits. What is this? Mass of this circular lamina here. This is lambda upon 2. Putting A here, this is A4 upon 2 minus A4 upon 4. That means A4 upon 4. Lambda upon 2 into A4 upon 4. That means lambda A4 upon 8. Okay, 8. This is the mass here. If I separate this mass into length, this is to be written in terms of this and the distance. Therefore, Mi, moment of inertia, is equal to mass into perpendicular distance, mass into r square, or we can say r square, m into r square. That means m let me, this is mass here. If I write lambda, this lambda A6, that means this is nothing but lambda A4 upon 8 into A square upon 3. So this R square is A square upon 3, while mass is lambda A4 upon 8 is 24 total. Lambda A6 multiplying, it will be lambda into A4 into 8 square is A6, lambda A6 upon 24. So this is the value here. Okay, so this is the final value. Mi, this is just equal to this. Okay, so this is the final answer. Mi is this. Either this is the answer, this is the same answer. Lambda A6 upon 24. Lambda A6 upon 24, this is the mass here. Mass is here. A square upon 3 is the perpendicular distance of this from the axis of x. Okay, in the first quadrant of the circle, x square plus y square plus a square, surface density varies as x, y. Find its moment of inertia about the x-axis. We have not to find out the mass and something. We have just separated this. This is the process of solving the questions. If I have to find out the mass and or radius of gyration, we will find out the radius of gyration. This is question number 16. Now let me take next question. What about seventh question C? Let me check. Now question number 7. Okay, question number 7 is of what kind? Okay. Question number 7. What does it say? Let me check it. Okay, now question number 7 is, this is show that the Mi, moment of inertia, of a thin uniform rod of mass m and length 2a, okay, about an axis through a perpendicular to the rod is m into 4a square, okay, perpendicular to the rod is m into 4a square upon 3. This we have to do. This is about one axis. Let me take axis of x. Then we have to find out. So this is what? There is a rod here. Let me take this rod. Okay, this is suppose rod here. Okay, and this is along the axis of x. Okay, if I take this OP up to this point, let me take OP, and this is Q here. Q is ds, and this is x distance. Okay. Now, this is about the axis of x. Now, about the axis of x, if I take this is the this is the axis of x, or if I take this is the axis of x. O, and this is y here. Axis of y, this is y dash, and this is x dash. Okay, so what is the mass given to us? Mass is m here. So that the Mi of a thin uniform rod of mass m and length twice a, length of this twice a, total length of the rod equal to twice a, mass of it equal to m. What is the elementary mass? M upon twice a. This is mass of this rod. And if I have to find out about the y x-axis, so that the Mi of a thin uniform rod of mass length this one about an axis, let me take this x-axis through a perpendicular to the rod is this. So perpendicular to the rod. Now if there is a rod, there is a perpendicular, which is perpendicular to the rod given here. What the length of this? Let me take what is given here, 7th question. So given here a rod of length V and the mass is equal to m, total rod. If I find out elementary, let an elementary P is equal to x and PQ equal to dx. Okay. If I have to find out this with respect to x or with respect to x here, then what is the MI? Therefore, MI is the solution we are finding out. MI of the rod about, let me take about x-axis. About x-axis will be how much? It says we take m into dx upon twice a. M upon twice a is the elementary mass into dx into factor square. Limits is 0 to 2a. Total length is 0 to 2. Limits, if I find out 0 to 2a total length. This is along the axis of x. Okay, and perpendicular distance of this from the x-axis. Suppose this is here y, or it will be y square. This is y square, and here it is dx. I'm sorry, this is dy here. First is with respect to x-axis, so this is y square into dy. Okay, so if I have to put these limits, what are these limits here? Integration. Here, distance of this length is y square into dy. So that we find out this m upon twice a constant. This is the elementary mass of the rod, m upon twice a element that I have taken out of this. Twice a, will be twice into y square into dy. If I integrate this with respect to x, we are finding the distance. If I take P point here, which is xy. Okay, then this is going to m upon twice a into y cube upon 3. Okay, limits 0 to 2. What was this? This is m upon 3, let me take outside into y cube. If I substitute, this is twice a whole cube. It will give us m upon 3 into twice a into 8a cube. For 2 whole cube is 8. It will give us m into this 2 portions a square. This is m upon 3 into 4a square. So this is m into 4a square upon 3. This is about x-axis. This is about one of the axes is x-axis here. Okay, so this is perpendicular length. Now, if I have to take this limits, about y-axis, so this is 2b, that about the rod is this m into 4a square upon 3. Okay, this is the mass of the, this is M.I., moment of inertia, M.I, about x-axis. About x-axis. And about y-axis, if I find out, so if I take this middle point of this, okay, as the origin, or let me take the rod is from this point to this point, length of this will be minus a to plus a. If I take this as origin, y-axis is this. This is y-axis passing through this middle point of this. If I take middle point, okay, so let me take the rod here. So the middle point of this rod is O. Length is, total length is a. O. This is minus a. This is plus a. Okay, and then this is along the y-axis. The limits of y-axis of if I have to find out about the y-axis, this is the length here. This length will vary from plus minus a to plus a. Limits are. So let me find out. This is about y-axis. This is root which is the answer here. This we have to prove about one of the axis, about an axis through a perpendicular to the rod. So at this rod there was a perpendicular here. This is the perpendicular. We have taken length, the y square. Okay, now we have taken x square, but limits will be now minus a to plus a. Why? Because we are taking this middle point as the origin of this point. Okay, so this rod is divided into two parts, minus a to plus a, total length twice a. Okay, so let me take that length here. So if we have to find out about y axis and y O is the middle point of y axis is this. Okay, so what is the moment of inertia of this rod about the y axis, means this length is there. If I have to take this x length here, and this is dx up to this point. Okay, so x dx. So x square and the okay, so mi about the x y axis, about the y axis, taking midpoint of rod as the origin. This will be equal to minus a to plus a, limit now minus a to plus a. But this x will vary from minus a to plus a, and this is m upon twice a again, elementary mass, length is twice a of this rod, and m upon twice a into x square into dx. Okay, so this has been solved now. This has been proved here. This mi about the axis perpendicular to the rod was this one, m upon 3 into 4a square. That was there. Now this let me solve. Here this is m upon twice a are taken common. If this minus a to plus a is to be changed, with twice into 0 to a. Try to understand. And this is x cube upon 3. I'm sorry, this is x square still. Okay, let me integrate it. X square is integrated as x cube upon 3, 0 to a limits twice we have taken, but when minus a to plus a, then this is definite integral formula. First, mi about the x-axis, mi about x-axis, which we have already calculated, which is m into 4a square upon 3. This is proved m 4a square upon 3. This was first equation. Of second we are calculating. This is not required here, but let me find out about the other x. This will be 2 to cancel out, m upon a into 3, okay, into a cube. The limit is a. So this is m into a square upon 3. This is about y axis. This is another answer. Okay, so this is one of the answers. This is answer option. This is the answer required. So these two are the answers. About the axis, this is about x-axis, this is about y-axis. If we add, this is the 4 times a square upon 3, this is only 1 time a square upon 3. So this we have taken as another point. So question number 7 we have done. Let me talk about now question number 8. What does question number 8 say? Let me check it. Okay, now question number 8 is of what kind? It says, find mi of a uniform rectangular lamina of sides twice a twice b and mass m about the axis of x and axis of y, and about an axis through O perpendicular to the plane of the lamina. This is, there are two things required. First, two axes, x-axis and y-axis, and then perpendicular to O. That means these two are to be added up. First, let me find out what is the uniform rectangular lamina of sides twice a twice b, mass n about the axis. If I get this is question number 8, let me talk about what is given to us. a rectangular lamina. This is a rectangular lamina of length and breadth of sides twice A and twice B. Twice A and twice B respectively, and mass M. And mass M capital. Okay, this is clear. About the axis we have to find out this, and then about O. O will be means we have to add the two. So what is the rectangular here? So let me find out the solution. First let me draw the figure. If I take a rectangular shape like this, okay, and the middle point, let me take this is the middle point, and this is the y-axis. The middle point of this are taken here, origin. This is x-axis, and this is y-axis. So this is twice B, and this is twice A here. Okay, this is length twice A, breadth is twice B. I've taken x-axis is this, y-axis is this. If I take a parallel strip parallel to the axis of x, sorry, axis of y here, so this is parallel to the axis of y. Here limits of y are 0 to twice b, we will take. And if I have to take this is the origin here, about this is x point here, this is suppose length of this is dx, dx length is this. Okay, so up to from origin to this is x here, x into dx we will take. Okay, then we have to first find out what is the MI, moment of inertia, about the axis of x. This is axis of x here. About the axis of x, if we have to find out, this will be y sphere. But about the axis of x, there is a point here that we take here, point pxy. Okay, so pxy, this is x coordinate, this is y coordinate up to this point. Now y is here along this y axis, this we have taken here. So this y will vary from minus b to plus b, and x will vary from either take minus a to plus a. Minus a to plus a we will take. Because this x, if I take x coordinate here,